So carbon is located in period 2, whereas iron is located in period 4. That means that carbon has fewer occupied electron shells, and iron has greater number of occupied electron shells, and that explains the difference in size between carbon and iron. So carbon atoms are smaller than iron atoms because carbon atoms have fewer occupied electron shells, and hopefully you can see that right next to carbon is the atom nitrogen. Also in period 2, nitrogen atoms are smaller than iron atoms because nitrogen atoms have fewer occupied electron shells. Welcome to AP Chemistry Review and Practice. My name is Michael Faribaugh, and I'll be your guide on the side as you strive toward that 5 on the AP Chemistry exam. Each episode will include answers and explanations to practice problems, along with advice to help you avoid common mistakes. So, are you ready to review and practice for the AP Chemistry exam? I hope so, because this lesson starts right now. Welcome back to AP Chemistry Review and Practice. In this lesson, I'll give you the chance to review and practice topics 2.3 and 2.4. As you can see on this slide, these topics fall under Unit 2 in the AP Chemistry curriculum, Compound Structure and Properties. You can add your comments and questions below this video, and you can also email me with your comments and questions at APChemistryReviewAndPractice@gmail.com. Check out the links in the video description area, which include the link to the packet that accompanies this video. Now let's move on to the review for topic 2.3, Structure of Ionic Solids. Here is an essential knowledge statement from the AP Chemistry course and exam description. The cations and anions in an ionic crystal are arranged in a systematic periodic three-dimensional array that maximizes the attractive forces among cations and anions while minimizing the repulsive forces. Now let's move on to the practice for topic 2.3. This is question 1. Question 1 asks, which of the following particle diagrams provides the best representation of a portion of a crystal of lithium chloride, LiCl? Now remember that opposite charges attract each other and like charges repel each other. So we need to minimize the repulsive forces. In order to minimize the repulsion between ions that have the same charge, instead of arranging the ions in rows, as you can see in this particle diagram on the left, the ions should be arranged in an alternating pattern for each row and column in the crystal lattice, as you can see in the diagram on the right. So based on this information, let's go ahead and eliminate choices A and C. There'd be too much repulsion between ions of the same charge. Now, to distinguish between choice B and D, which have the correct arrangement of the ions, let's consider the relative size of the lithium ion and the chloride ion. Let's take a look at the electron configuration for each ion. Now, lithium, the atom, has 3 electrons with an electron configuration of 1s2, 2s1. But since the lithium plus ion has lost an electron, the electron configuration would be for 2 electrons, 1s2. Chlorine, the atom, has 17 electrons with a configuration of 1s2, 2s2, 2p6, 3s2, and then finally 3p5. But since the chlorine with a negative charge has actually gained 1 more electron, its electron configuration with 18 electrons stops at 3p6. Well, hopefully you can see by comparing the electron configuration of Li plus and Cl minus that the Cl minus ion should have a larger size. So the chloride ion has a greater number of occupied electron shells, energy level 3, than the lithium ion, energy level 1. So therefore, the size of the chloride ion is larger than that of the lithium ion. And so that makes choice B the correct answer. Now, in question 2, it asks, which of the following correctly describes the conductivity of solid potassium bromide and provides a valid justification? Now, on this slide, this comes from one of my videos from Unit 4, in which I was talking about the conductivity of various substances. And it turns out that ionic solids, such as sodium chloride, do not conduct electricity. And here's why. Sodium chloride is an example of an ionic solid. There are positive and negative ions present in the solid, but they are held in fixed positions in a rigid crystal lattice. Since the ions, or these charged particles, are not free to move and flow, solid ionic compounds do not conduct electricity. So now we're looking here in question 2 for an answer that says does not conduct electricity. So it's either choice A or C. Now it's not because the solid potassium bromide contains neutral molecules. It's because the solid potassium bromide does contain ions, but the ions cannot move freely throughout the solid. So the correct answer to question 2 is choice C. Now let's take a look at question 3, in which we have to draw a particle diagram. So it says the particle level representation of a portion of a crystal of an ionic solid is shown below in the box on the left. Now, the intent of this diagram is to illustrate the brittleness of an ionic solid, which is the result of internal repulsion of ion layers within the crystal lattice. This repulsion occurs when the layers are displaced by an applied force parallel to the layers. So we have a before box in which a particle diagram is drawn, and then we have to draw the particle diagram for the after box. So in the box below on the right, draw the particle level representation of the crystal that illustrates the repulsion of the ion layers within the crystal lattice. Now in your drawing, represent cations and anions as indicated below with white and black circles. Now before I reveal the correct answer to question 3, I'd like to show you a short video involving the brittleness of an ionic solid.
Here, a small crystal of solid sodium chloride is shown. It is transparent and has 90-degree angles at the sides. When a knife blade is placed on it parallel to one side and tapped with a hammer, the crystal cleaves into 2 pieces, each with a very clean plain edge. Now the piece that was cleaved off of the original piece is examined. The knife blade is placed on it at a 45-degree angle to a side and tapped with a hammer. The crystal shatters, but part of it cleaves parallel to a side. In this atomic scale view of sodium chloride, when the crystal is struck, ions with the same charge are moved near each other. Since like charges repel, the crystal cleaves into 2 pieces along the plane where it was struck.
So your particle drawing should show repulsion between the ions of like charges that leads to separation of the layers. So here's an example of the particle drawing. I tried to put the black circles right on top of the black circles and the white circles on top of the white circles, and the arrows indicate the repulsion between the layers. So the particle drawing should indicate 2 adjacent layers of ions in which the ions of like charges are right next to each other, and this causes repulsion of the ion layers. Now let's move on to the review for topic 2.4, structure of metals and alloys. Here are some essential knowledge statements from the AP Chemistry course and exam description. Metallic bonding can be represented as an array of positive metal ions surrounded by delocalized valence electrons, that is, a sea of electrons. Interstitial alloys form between atoms of different radii, where the smaller atoms fill the interstitial spaces between the larger atoms. For example, steel, which contains carbon and iron, The carbon occupies the spaces in between the iron. On the other hand, substitutional alloys form between atoms of comparable radius, where one atom substitutes for the other in the lattice. For example, brass, which contains copper and zinc, they have roughly the same size, so zinc substitutes for copper. Now let's take a look at the practice for topic 2.4. This is question 4. In question 4, it says, a particulate diagram of a solid substance is shown above. Based on the information in the diagram, which of the following correctly describes the conductivity of the solid substance and provides a valid justification? Now, as you examine the features of this particulate diagram, you might not know at first if this is an ionic solid or a metallic solid. Now, we do see both positive charges and negative charges, but focus your attention on the negative charges in this particulate diagram. Notice how randomly they are arranged. This is not a regular array of positive and negative ions, and we can see labeled in this diagram a sea of electrons. So what we are looking at is a particulate diagram of a metallic solid. Metallic bonding can be represented as an array of positive metal ions surrounded by delocalized valence electrons, that is, a sea of electrons. So now we have to consider, is this metallic solid going to be a conductor of electricity? Now you may already know that metals are good conductors of electricity. Why? Because of the mobile charges, specifically the electrons. So the mobile valence electrons, that is the sea of electrons, is the reason why metals are good conductors of electricity. The electrons are free to move throughout the solid. So now in question 4, we're looking for choices that say, yes, it does conduct electricity, which is either choice A or B, but the correct answer is choice B. So the problem with the justification in choice A is it doesn't explain enough. It simply says the substance contains positive and negative particles. And as we already saw in topic 2.3, the ionic solids contain positive and negative ions, but then those charged particles are in that rigid crystal lattice. They're not free to move around, and therefore ionic solids do not conduct electricity. So just simply stating that a substance contains positive and negative particles is not a sufficient justification to explain conductivity. For conductivity, you have to talk about mobile charges. Specifically, in this case, it would be the mobility of the electrons. All right, well, that is the correct answer to question 4, choice B. Now let's take a look at alloys in question 5. We have to talk about the difference between interstitial and substitutional alloys. So question 5 says the following. Which of the following identifies the type of alloy that would be likely formed between atoms of iron and nitrogen and provides the best particle level representation of this type of alloy? So you may recall that the essential knowledge statement for interstitial alloys mentions steel. Well, steel contains iron and carbon. Let's look on the periodic table to see where these elements are located. So carbon is located in period 2, whereas iron is located in period 4. That means that carbon has fewer occupied electron shells, and iron has greater number of occupied electron shells, and that explains the difference in size between carbon and iron. So carbon atoms are smaller than iron atoms because carbon atoms have fewer occupied electron shells, and hopefully you can see that right next to carbon is the atom nitrogen. Also in period 2, nitrogen atoms are smaller than iron atoms because nitrogen atoms have fewer occupied electron shells. So what are we looking for in question 5? We're looking for interstitial alloy. So we're looking for either choice A or B. Hopefully you can see that the particle level representation in choice B is incorrect. That would be the particle level representation of a substitutional alloy, where the atoms have comparable sizes. We're looking for an interstitial alloy, where the smaller atoms can fill in the spaces between the larger atoms. So So that makes choice A the correct answer to question 5. Now let's move on to the portion of the lesson where I give you advice to help you avoid common mistakes. Now, my first piece of advice is something that I always say, and you've heard me mention this in previous episodes of AP Chemistry Review and Practice. Read the question carefully and make sure you are answering the question that is being asked. My next piece of advice is specific to topic 2.3, ionic solids. Be familiar with particle level representations of ionic solids as shown in the examples below. Now you'll notice that some of these particulate diagrams have particles with different sizes. So my next piece of advice is your knowledge of electron configurations, topic 1.5, and periodic trends, topic 1.7, may be needed when comparing the relative sizes of atoms or ions in particle diagrams involving ionic compounds or metal alloys. Now I'd like to talk about conductivity. So in order for a substance to behave as a conductor of electricity, it must meet both of the following requirements. There must be charged particles present in the substance, and the charged particles must be mobile and free to move throughout the substance. Also, be specific with your language. There is a difference between electrons and ions. So therefore, make sure you use the correct term when you are discussing the conductivity of a substance. The following chart summarizes the conductivity of ionic compounds and metals. So let's start with a metallic solid. Can it conduct electricity? Yes. Why? Because there are delocalized valence electrons, a sea of electrons, and these electrons are free to move throughout the metallic solid. Now, can an ionic solid conduct electricity? No. Why not? Because although there are positive and negative ions present in the solid, these ions are not free to move throughout the solid. Now, we didn't see any examples in this lesson about taking an ionic compound and melting it or dissolving it in a solvent, but if you were to do that, if you were to take an ionic compound and either melt it or dissolve it in a solvent, usually water, to form a solution, then yes, that would conduct electricity, because now the positive and negative ions, either in the molten sample or throughout the aqueous solution, would be free to move. So a molten ionic compound or a solution of an ionic compound does conduct electricity. Now, note that we will explore properties of ionic solids and metallic solids in a future episode that includes topic 3.2, properties of solids. One property of an ionic solid mentioned in this lesson is brittleness. The brittleness of ionic solids is due to the internal repulsion of ion layers within the crystal lattice that occurs when the layers are displaced by an outside force parallel to the layers and they move relative to adjacent layers. And then finally, there are two types of metal alloys. Interstitial alloys form between atoms that have different sizes. The smaller atoms fill in the spaces between the larger atoms, as we saw with carbon and iron in steel. And then substitutional alloys form between atoms that have comparable or similar sizes. And one example would be brass, where copper and zinc have similar sizes. So now we have come to the end of the lesson. In my next lesson, I'll give you the chance to review and practice topics 2.5 to 2.7. If you enjoyed this lesson, I invite you to like this video and subscribe to my YouTube channel. Check out the links in the video description area, which include the link to my YouTube playlist organized by AP Chemistry's CED units. You can add your comments and questions below this video, and you can also email me with your comments and questions at APChemistryReviewAndPractice@gmail.com. Thank you for letting me be your guide on the side as you strive toward that 5 on the AP Chemistry exam. Keep studying, and I'll see you next time on AP Chemistry Review and Practice.